Hi folks, this is lesson 3 in our series of videos on trig functions for students in year 12 who are studying A-level maths. So the previous 2 videos we looked at sketching the graph of sine, cos and tan, and then we looked at some simple transformations. Today we're going to look at the connection between sine, cos and tan and the unit circle. Okay, so let's start off with a circle. The unit circle gets its name because it has a radius of 1, so a unitary radius. There's the radius there. It's got some special properties. So the unit circle is placed, the centre is placed at the origin. There we go. And there's a point P that lies on the circumference of this circle. So let's put that point P on our diagram as well. There we go. Now what we're going to do is think about how we can describe the position of point P as it moves around the circle. So we could, if we wanted to, use Cartesian coordinates, the coordinate system that you already know about. If we say that P is at the point x, y, then this distance will be x, and this distance will be y. But alternatively, we could think about the angle that the point P makes. If we work out the angle between this line and the positive x-axis and call that theta, that would be another way of describing where that point P is. So if we put those two systems together, then we get a fairly familiar diagram that you probably recognise. There's the angle system, and there's the Cartesian system, and we get a nice right angle triangle with an angle theta, which we can do some trigonometry on. So we're saying that we always measure the angle from the x-axis, from the positive side of the x-axis, and anti-clockwise is positive. So if we went round 90 degrees, we'd be up here at the y-axis. Another 90 degrees would take us over here to the negative x-axis. If we're at 270, that would be the negative y-axis. And if we did a full turn, we'd get back to the positive x-axis. Okay, at this point it's probably worse. Switching out from PowerPoint to some software called GeoGebra. This is free software that you could download, or you can run it in a browser. You can make yourself an account and have a play. I built this unit circle diagram using a video on YouTube, and I've put the link there at the bottom. If you want to have a go at building your own, it's quite an interesting hour to put that together. I would recommend it, actually. It'd be a good thing to do. Help you understanding of how the unit circle links with trigonometry. So let's switch to that now and have a look at it. Okay, so here's my unit circle again. You can see it's here, centered at the origin. Now I've got a couple of slider bars to show you. So the first one is just varying the radius of the circle between 0. If I slide to the left, it goes down to 0, and we can make it up to 5. But let's put it back at 1. We're interested in the unit circle, so radius has to be 1. Let's put it back to 1. So there we go. Okay, and the other slider bar is this angle theta that we talked about earlier. It's the angle that the point P makes with the positive x-axis. So if I slowly scroll this to the right, you should see that point P moves around our unit circle. So there's 90 degrees, 180, 270, and there's a full circle. Okay, let's scroll it back again to 0. Okay, so what I want you to do is to look at the orange line. The orange line is the height of the point P above the x-axis, and focus on that. As I scroll this scroll bar, have a look at the height of that line. So it starts off with the height of 0, gradually works its way up to be a height of 1, and then as we move from 90 to 180, the height decreases back down to 0, and then we've got a negative height here. increases as we scroll towards 270. Sorry, I should say decreases towards -1, shouldn't I? And then back up to 0 as we continue round a circle to 360 degrees. Now, hopefully that starts to ring a bell with you in terms of the connection between that and the sine function. Let's have a think about that again. Yeah, so it goes from 0 to 1, back to 0, down to -1, back up to 0. That sounds like the sine function to me. What I can do is to plot a point to try and help you see the connection. So if I switch on my point, it's point D on the graph. This point D is plotting in the x-axis. Its x-coordinate is the angle in radians, actually, not degrees, but in radians that P makes. So as I move this, let's get it to 0, we can see that we've got an angle of 0, so D's on the origin. And the other part, the y-coordinate of D, is the height that P is above the x-axis. So as I move from theta equals 0 to up to theta equals 90, hopefully you'll see the height of D matches the height of P. So very much at the top there, it becomes 1. Okay, and that's at 90 degrees. I feel like pi over 2. If we keep going, height of D should come back down to 0 when our angle gets to pi. Okay, and if we keep going through, hopefully you can see that that point D is mapping out the sine graph. Can you see that? Hope that makes sense. So all we're looking at is plotting the height of the point P above or below the x-axis. Okay, so hopefully you can see there's a huge connection between the height of P, or if we just say what its y coordinate, and the sine function. Alright, it might be worth as well looking at what happens if we go past 360 degrees. So if we go through one full cycle of the sine graph, one full wavelength, 180, 270, 360, all that happens in our unit circle is that the whole process continues again. So if we go again round, we're going to get the same thing again. And same thing happens as well if we go negative. So if we look at a negative angle, if we go to, for example, there we are at theta equals 0 again. If we look at, say, negative 45, I can't quite hit. Let's see if I can hit negative 90 then. Let's have negative 90. There we go. So negative 90 degrees is the same on our diagram as 270 degrees. Okay, so hopefully I've convinced you that by thinking about the point P and where it is, height of P, the y value, maps out the sine function. Let's switch that point off. And now let's start thinking about the distance of this red line, this distance between the point P and the y-axis, or the point 0, 0. Let's think about that distance. So we're just looking at the horizontal distance now. Okay, and this point F is similar to the last point. It's plotting out the horizontal distance against angle. So angle across in the x direction, and the horizontal distance is now a y value for F. So at the minute we're at here, theta equals 0. Our horizontal distance is 1. That's why F is up there at 1. When the angle is 0. Now then, let's scroll that forwards. We move the point P around the circle. Look what happens to that point F. What's it doing? Okay, so hopefully that pattern, that route that F is taking, is a familiar pattern to you. Hopefully you can spot that that is pretty much just the cosine curve. Starts off at 1, when the angle is 90 degrees, we get a 0. At 180, we're on -1. There is it. Get it right. There we are. At 270, we're at 0. And at 360, we're back up to 1. So there's another connection then. The connection between the horizontal value, which is the x value of p, is linked to the cosine curve, cos theta. Okay. And then finally, we've talked about sine and we've talked about cos. Let's talk about tan. So, tan, if I can park that back on 0. There we go. Nearly, that'll do. Tan, there we go, point, is basically the gradient of our blue line, the line that goes from O to P. So, if we start off down here, this line has got a gradient of 0, change in y over change in x. If we can take it up to about, where's that angle there? We can get close to 45, might not hit it exactly, but there we go, that's pretty close to 45. This is gradient is just above 1. 45 degrees would be exactly a gradient of 1. If we keep going, hopefully you can see, I'll do this more slowly so you can see, let's go slowly from 0 to 90 degrees. You can see the point G maps out another familiar curve going off up there. The gradient's getting very steep and it goes off the plot. And then for a second there it's coming back down. Goes through pi. Another asymptote there. And again, hopefully that pattern that you just saw, that G mapped out, looks familiar too. It looks like the tangent graph. Okay, so yeah, this is really useful bit of software GeoGebra, and I would definitely encourage anybody that wants to get on and make one of these little unit circle diagrams in GeoGebra using the video on the link. Okay, so let's get back to our PowerPoint. So let's see if we can try and summarize what we found out there. We can use the unit circle to give us the definitions of sine, cos, and tan. And if we look at the connection, sine theta, as we know, is opposite over hypotenuse. If you look at this direction here, the opposite is y, and the hypotenuse is 1. So we get sine theta is y over 1, or if you like, the y is sine theta. And we saw that on the diagram, to me, the height of point P maps out the graph of sine theta. If we look at cos theta, adjacent over hypotenuse, that's x over 1. That tells us then that x is cos theta. And we saw that again on our unit circle diagram in GeoGebra, that cos theta was mapped out if we considered the horizontal part of the point P, the x value. And finally, tan theta is opposite over adjacent, so that's y over x, which is the same thing as the gradient of the line. And we saw that again by looking at some of the gradients. Okay, let's see if we can use this then. So we can use the unit circle for all sorts of useful stuff. It comes in handy for finding key points on trig graphs, but it also comes in really handy when we're solving trig equations, and we'll come on to that in a later video. Let's use it here to find some key points. So let's look at sine 90 degrees. See if we can get a pointer on here. Okay, so where would 90 degrees be in our diagram? If we start measuring from the positive x-axis, theta at 90 degrees would be up here. So this is the point here where we'd be. And for sine, we're considering the y value, aren't we? So what would the y value be at that point? Well, hopefully you can figure it out. It's 1, isn't it? There we go. That's sine 180. So sine of 180 is around here. I'm going to get to this point here. What would the y value be? 0. Sine of 270. And again, thinking about the y value for sines. -1. Let's think about cos 180. So cos 180 would be over here. And this time we're thinking about the x value. What's the x value there? -1. Cos of -90. So again, we talked about what would happen if, because we talked about measuring from the x-axis and anti-clockwise being positive. To get to -90, then if we start off at the x-axis, to get to -90 we'd come down here 90 degrees. So we're at this point, -1 here. And our cos is the x value. So we think, what's the x value at that point down there? The point 0 -1. So the x value is 0. And again, we talked about what happened if you did more than one full circle of the unit circle. So if we start over here and we do 0, 90, 180, 270, all the way around by 360. To get to 450, we need to go another 90 degrees, which takes us up to here. So we've done a full lap of the unit circle plus another 90 degrees. And again, our x value is cos, isn't it? So cos would be 0 at that point. Hope you got those right. Okay, so let's look at example 2. Use the unit circle to find tan of 45 degrees. In one of our next videos, we'll look at the exact values for some trig functions. Until then, I'm just going to give you this point. When theta is at 45 degrees, up here, this point is the point 1/√2, 1/√2. So the x and y values are both the same, 1/√2. Remember, tan is to do with the gradient or the slope of this line, which is given by y over x. So if we do y, which is 1/√2, divided by x, which is also 1/√2, y over x is 1. So tan 45 is 1. Let's think about tan of 135. So 135 is going to be over here. Think about the slope of that line that connects the origin to that point over here. What's the slope going to be? -1. Excellent. Okay. Tan of 225 is down here. And again, thinking about the gradient, the slope of that line, hopefully you can see that that would be 1. Tan of -45. Remember we said that anti-clockwise angles are positive. So if we want to measure tan of -45, we've got to go clockwise 45 degrees, takes us down to here, which is the same as tan of 315 degrees. And that slope there is a negative slope, so it's -1. Tan of 180. So 180, we're going to be over here. Think of the change in y over the change in x. Well, the y value is 0 and the x value is -1. So at that point, anything 0 divided by anything is going to be 0. So tan of 180 is 0. And then let's think of tan of 90 degrees. Okay, so 90 degrees is up here. And again, think of the y over x. So this time the y is 1 and the x value is 0. And as you know, we'll get a problem whenever we try and divide by 0 in maths. That 1 divided by 0, try to type it in your calculator, it will be undefined. So that's why tan 90 is undefined. We can't divide by 0. Okay, well I hope that's been a useful introductory lesson on the unit circle. We're going to be using it for the next few lessons, so make sure you're totally up to speed with it all. Just to summarise, the x and the y values of p, the point on the unit circle, are linked to the functions of sine, cos and tan. We can use the unit circle like we've just been doing to quickly find points on trig graphs, and we'll come on and use the unit circle a lot when we're solving trig equations. That's it for now. Thank you.